Okay, in this podcast we're going to talk about heating curves, and most of this should be a review from Honors Chem. If you recall, every substance has a heating curve that looks exactly the same as any other substance, has the same shape. Now this is a physical change, right? I'm just changing phase from solid, liquid to gas. Or I could draw a cooling curve which would parallel this one coming down, right? And we always start with the solid at the low temperature. We add heat. Sometimes we say time over some heat. And as we do that, the same things happen in all substances. Okay. So let's take a beaker. We put some ice in it and we start to heat it up. Now this is a phase diagram. I didn't show these last year. Maybe your teacher did. This is actually something that's going away in the curriculum next year for AP, but it might show up this year. And it's similar to the heating curve. What you have here is you have to orient yourself. Here we have temperature, and here we have pressure. So at the lowest temperature, this green area, that's going to be your solid. The warmer area is going to be a liquid, and this whole area is going to be the gas. And each substance has a little different shape, but for the most part, you can orient yourself by the thing on the leftmost side of the chart is going to be your solid, and the rightmost side is going to be your gas, because this is a temperature line. So we're going to watch what happens to both the phase diagram and the heating curve as we heat up this beaker of water. So here we are on the phase diagram. We moved along this line, so we are still in the solid phase. Temperature is going up, pressure is staying the same. Okay, we've hit the line between solid and liquid. In the heating curve, here we are looking at heat added and the effect it has on temperature. So the temperature has risen, but we still have ice. In the next part of the curve, interestingly, the heating curve, we move along this line as time goes by, but there's no change here. Temperature and pressure are staying the same. And that is because when we are at this plateau, what is happening is the solid is melting. And during that process, there is no change in temperature. The temperature is not rising, contrary to what most people would expect. So let's take a little closer look at what's happening. So during this time, where the phase change is taking place, the melting is taking place, we call the heat involved with that the heat of fusion, because it's actually the same quantity of heat, just an opposite sign, as if it were going the opposite way, if we're going from a liquid to a solid. And solid you can think about as fusing molecules together. That's where it got its name, heat of fusion. So we use that in our calculations here when we have a phase change going on, a melting or a freezing. Okay. So why do we have to expend energy to make that phase change occur? Why is the temperature not going up? Well, it turns out water, as you know, is very polar, and there's a lot of hydrogen bonding between water molecules forming this whole lattice, and you need energy to break these attraction between water molecules. So that takes some time, right? It takes some energy, some heat, it takes some time for that to happen. Okay. Alright, so if we're looking at starting as a solid, it heats up until it reaches the point where it's high enough temperature for the water molecules to start separating from each other. And during that time in the beaker you have a combination of liquid and solid. In the middle here you'd have some of both. At the very start you have all solid. At the very end you have all liquid. Okay. After this point, what happens now is in the phase diagram, the temperature increases again. Here the temperature is increasing. We're no longer going through a phase change. We have all liquid water here, and it is rising in temperature. You can see the temperature going up. Okay? Until we get here. When we get here, phase change occurs again. We go from liquid to gas, in the phase change called boiling or vaporization. And we have both liquid and gas in the beaker at that time. And here we are on the liquid-solid line in the phase diagram. This we call the heat of vaporization. This is where we're vaporizing. It's where there's no temperature change. It's at a phase change. And we can look those up for each substance, just like we can look them up for the heat of fusion. Okay, so we need temperature at this point. I mean, the temperature is being used to raise the temperature. Molecules are moving faster. That's what's happening. So no temperature is rising on this flat part, but once we pass this flat part and add more heat, more energy, the temperature starts to rise. And you see this movement against the gas. Here we're all gas, but the temperature of the gas is rising. So when we're on the flat parts, the temperature is not changing. We have heat of fusion, heat of vaporization. We have temperature increasing when we're on a slope. You can see the temperature rising, right? Okay, so let's answer a couple questions. In winter, the most northern lakes contain both ice and liquid. Click on the part of the heating curve that corresponds to the situation, and that would be right here. You always orient yourself. Down here, low temperature, solid, liquid, gas. Here we're between the two, so we have solid and liquid. Let's try another. Water vapor is actually invisible. However, you can see steam as it emerges from a teapot. Click on the part of the heating curve that explains why you can see steam emerging from a teapot. Whoops, that's incorrect. What do they say? Steam emerging. So if steam's emerging, good catch. It's happening here. I have both liquid and gas, but this is when I start to see vapor rising. When I reach here, I have no more liquid in the pot. It is all vapor. Okay, let's do one more. Since the freezing point of water is 0, ice made from pure water can never be colder than 0. Well, in fact, it can be. Right down here, we go below 0. So that would be false. All right. Now let's look at some heating curves over here. And I'm going to go all the way up. And here you want to use the diagrams I gave you if you want to take some notes on here. Alright, so we're saying as we add energy or we're adding time over a Bunsen burner, all substances have the same shape for their heating curve. It will start off as a solid down here, low temperature, temperature rises. We have liquid here, the highest temperature we're going to have the gas. Okay. At this first plateau here, we go over to the temperature axis. We will see what is known as the melting or freezing point. This is the temperature that melting and freezing both occur. Likewise, if we extend this to the temperature line, we see the boiling and condensation point. And these are temperatures. For water, this is 100 degrees Celsius. Different substances have different boiling and melting points. This is the temperature at which something melts or freezes. For water, it's 0 degrees Celsius. And you do need to know that. Water melts and freezes at 0 and boils and condenses at 100 C. And the phase changes occur along the plateaus. All the energy is being used to break attractions, so none of it is available to increase the temperature. That's the key point on phase change heating curves, is all the energy goes into changing the phase. None of that energy is available to increase the temperature. Okay, so let's take a look at a couple of actual problems. Okay. Change in temperature of a solid absorbing energy. We're going to use this formula, Q equals MC change in T. Okay, when we get to the plateau, we no longer have a change in temperature, so this change in temperature would be 0. So we are going to use something that has mass times some other constant. Okay? And so here we're going to use the heat of fusion. This is a value, again, you can look up. And it depends on your C. If your C is joules per gram, you're going to use heat of fusion times grams. Or if your heat of fusion is kilojoules per grams, you're going to use grams. If it's kilojoules per moles, you're going to use moles here. Okay, so it depends what you're given in your units. Temperature rises. When temperature is rising, I'm going to use this formula. Okay. I reach the next plateau. There's no temperature change, so I'm going to go back and use some delta H in number of moles or grams, depending on the units of my constant. Okay. We call this the heat of vaporization. And once we get to vapor being heated, again, I have a temperature change, so I can use this equation. Okay. Alright, so let's take a look at an actual problem. What is the total energy for 10 grams of water with a total change in temperature from minus 20 to plus 50? Now, I always told my students the best thing you can do is identify where you are on the graph. If I'm at minus 20, water freezes right here, or melts right here. So if I'm minus 20, this is 0, I'm going to be down here. And if I get to 50, I'm going to be halfway between melted and boiling, so I'm going to be right here. So I want to calculate my energy starting here and going all the way up to here. Let's take a look at how we do that. So we identify where we're starting and where we're finishing and any key phase changes, right? We have our constants, we've looked those up. So we need to calculate the energy change to take it from minus 20 to 0, which is the temperature at which the phase change occurs. We've got to figure out what this is going to be. When we get to melting, we have to use a different equation, the heat of fusion times the number of moles or grams, depending on our constant. And then we need a third Q for rising temperature of the liquid. Okay? Because the temperature is rising, we're going to use this formula again. So here we have 10 grams. Our difference in temperature is 20 degrees. Now there's different heat of or specific heats for water depending on the state of matter. So it's different for ice, solid, than it is for liquid, which is why I have 2.1 joules per gram. Change of temperature is 20 degrees C. Okay? Q2, 10 grams. I look up my value for heat of fusion and plug that in. Okay? And then Q3, again, this should be 4.184 joules per gram degree C for water, liquid water. I have 10 grams, and I'm going up 50 degrees. It's 0 degrees C here when it just begins to start rising in temperature, and I go up to 50. So I calculate each of these, and then I have to add them together. My total heat is going to be my heat 1 plus my heat 2 plus my heat 3. And that's what I get for my total. So it takes 5,800 joules to heat 10 grams of water from minus 20 to plus 50. Identify where I'm starting, identify where I'm ending, and that's the total energy it takes to do that. Okay, I'm going to stop right there.